Okay, this is the next video in our wave unit, and it is about wave properties, or how Mr. Bell shreds on Jingle Bells. If you don't understand the reference, it's because you weren't here during Christmas and you're not in a learning community, but whatever. So, the objectives of this unit is that by the end, you are responsible for being able to do all of these things, which means if there's a quiz, you should be able to do all these things on that quiz. And that would be define and apply the terms longitudinal, transverse, mechanical, pulse, periodic, compression, rarefaction, amplitude, wavelength, crest, and trough. I know there's a lot of words. And then calculate the velocity of a wave, and then understand the main source of wave energy. So question, what do the ocean, the sound of a whale, and a lighthouse have in common? And the answer is they are all examples of waves. And a wave is anything that causes a disturbance and is tied to a motion. So a wave is just the motion of a disturbance. So for example, if you're like looking out on a lake and you see little water droplets or like a pond and something splashes in the pond, that's a disturbance. And that creates a motion of disturbance that ripples throughout the lake, and that's what a wave is. So anything that causes a disturbance can be a type of wave, or anything that causes something that fluctuates is considered a wave. And so there are many, many types of waves, and we're going to talk about really like 3 different kind of classifications, and each of these classifications have 2 types. So the first, and really all of these just kind of have like questions. So the first kind of classification is medium. And so does the wave require a medium to travel through? And so like water would be an example of a medium, or air would be an example of a medium, just something for it to like actually physically travel through. If the answer is yes, then we call that a mechanical wave. So for example, this guy doing his little fancy exercises using these ropes by making waves in the ropes, it requires the rope, so it's a mechanical wave. If it doesn't require matter as a medium, then it's electromagnetic, because light is electromagnetic and it doesn't require matter. It can go straight through empty space or a vacuum. It doesn't have to have air present like sound and other mechanical waves do. Okay. The second classification would be, how does this disturbance occur? Because remember, a wave is just a disturbance. So if the disturbance or motion is parallel to the motion, like the direction of the movement of the wave, then we call that longitudinal, because think of like the word longitude is like a parallel line that wraps around the earth. So if it's parallel to your motion, we call that a longitudinal wave. And so an example would be sound and slinkies. Think of like a slinky. If you like pulse little compressions through it, they will travel along the direction of the slinky. And that's parallel to its motion, like it's moving this way and it like is vibrating like this as it goes down the slinky. Okay. The other option is that it's perpendicular to motion, and all simple harmonic motion falls under this category. And that would be called transverse. And so it's because it's moving up and down while it's moving sideways. So that's perpendicular to its motion. So it moves and you end up getting sine waves with transverse. And so examples would be ropes, water waves, like if you go to the beach, light is a transverse wave, and sine waves. Anything that's going to make this pattern is considered transverse. So the third type, or third category is, so far we have mechanical and electromagnetic, longitudinal, transverse, and so our third category is, how long does this disturbance occur? And like really what is going on? If the disturbance only occurs once, like you throw a rock in a pond, that's called a pulse wave, where you just have one little single pulse travel through. So this guy creates a small pulse in a rope attached to a wall. And so it's not occurring over and over. It just occurs once. The other option is that it is regularly or periodically occurring, and so we call it a periodic wave. So like in class, if something is like happening over and over and over, like think of a lot of pulses, many pulses create a periodic wave pattern. And again, it looks like a sine. Okay, So now we're going to need to fill in some vocab into these kinds of waves, and we're going to use this vocab for the next 2 units. So it's really important that you understand what each of these terms means. So first of all, this is called a trough. Okay, a trough is either for like putting plants in or often used for feeding animals, but it's like a bowl, like a long like bowl that you put food in. Okay, this is called a hill crest. Notice like the top of a hill is called the crest of a hill. And so this little cow is grazing on the crest of a hill. So when people first started like talking about waves, they called the top of a hill the crest, and they called the bottom of a hill a trough, because this looks like a bowl and this looks like a hill. So the crest and the trough. And then the distance between 2 crests, or really 2 places on any 2 places on the same wave. So like here and here, or the crest to crest, trough to another trough, is called the wave length. And it's literally just the length of the wave. Okay, and we use this little funky letter. If you play Half-Life, then you recognize this, but it's called a lambda. Kind of like a little lamb grazes on top of the crest of a hill. It's called a lambda. Okay, and then our last word is that if this is our equilibrium line, right, where it's going up and down, kind of like the spring, then these 2 heights would be considered amplitude. So the distance from equilibrium to the highest or the lowest point is the amplitude of a wave. Okay, for longitudinal waves, we have a kind of different terminology. Okay, so first of all, this is a animated file showing you kind of what a longitudinal wave looks like, maybe like over a plane instead of just in a slinky. But notice that you have like these lines compressing, and it travels through, this compression travels through in perpendicular to the direction that it's actually moving, or sorry, parallel, right? Longitudinal is parallel. But it's not like waving up and down, right, like a sine wave. It's just kind of like compressing and moving in the same direction. Okay? And so this is often with sound. And so sound basically causes these areas of really compressed air. And this kind of like waves and travels from the speaker to your ear. And next unit that we do is sound. And so we will talk about this in much greater detail in a second. But if this is your slinky longitudinal wave, then the wavelength is again from one compression to another. And so basically, instead of having crests and troughs, now you have compressions, which are areas of high concentration, and then you have rarefactions, which are areas of very low concentration. And the way I always remember this is because during a rarefaction, it is very rare. Like you don't see very many slinky coils together because they're rare. And so rarefaction is when it's not very clumped. Compression is when it's really clumped. And a wavelength is from one compression to another, or one rarefaction to another rarefaction. Okay, and longitudinal waves are almost always caused by compression. And then amplitude is the amount of compression, how squished it is. So instead of like height being amplitude, amplitude for a longitudinal wave is how dense is this compression right here. Okay, and so for a wave, it's really easy to find velocity, because if you think about it, velocity is distance over time. And so the distance that a wave travels is technically wavelength, and the time it takes to travel would be one period of a wave. So you have lambda divided by capital T, think of period, okay? And so if frequency is 1 over period, and I have a 1 over period here, then the velocity of a wave is the wavelength times the frequency. And velocity is in meters per second, wavelength is in meters, frequency is in hertz, but remember it also is like 1 over seconds. So meters times 1 over seconds is meters per second. That all works and matches. And lastly, for the energy of a wave, okay, waves primarily transfer energy. If you think about it, like the sun is an example of light waves, and they carry a lot of energy. And if you don't believe me that other waves don't carry energy, just go to Mission Beach in San Diego and spend an afternoon getting pummeled into the sand by these 10-foot waves, and you will definitely remember that waves have a lot of energy. Or you can just think of all the tsunamis that, displace millions of people from their homes. So waves do carry an incredibly high amount of energy. And this wave energy is based on amplitude. If you think about a tsunami versus a small beach wave, the difference is that a tsunami has a huge amplitude, a huge height to its wave, and that carries a lot of energy. In fact, the energy is proportional. That's what this little guy means, this weird half infinity. Energy is proportional to the square of the amplitude. So if you double the amplitude, the energy goes up by 4, like 4 times greater. So that's why tsunamis are so devastating, because they carry a lot of energy. Okay? And then if you think of a guitar amplifier, the word amplifier comes from the fact that you are increasing amplitude, which obviously is going to give you more energy. So the answer to the question, how can Mr. Bell shred on his guitar and play Jingle Bells for fundraisers, is because that he can increase the amplitude of his sound waves using an amplifier. So there you go. And that is the end of this video, and we will talk about this more in class.